All right, welcome back to our continuing discussion of the non-visual senses. This time we're talking about touch, our somatosenses. So our somatosenses are our senses of the body, more or less. We have our cutaneous senses, which are what you might traditionally think of as your sense of touch, right? If you're talking about the five senses, we would talk about touch, things you can, feel with your skin. Touch, vibration, temperature. We'll talk about all of that. We also have proprioception, which is your awareness of the position and posture of your body, and kinesthesia, which is your awareness of the movements of your body. Okay, let's talk through the different sorts of cutaneous sense receptors that we have. So here we have hairy skin, which is most of the skin on your body that has some amount of hair on it. Glabrous skin is the sort of it's skin without hair on it. So things like the palms of your feet and your hands would be glabrous skin. So here in white, we have pictured the free nerve endings. These are what they sound like. They're nerve endings. They're not encapsulated. These detect a number of different things, including thermal stimuli, noxious stimuli, including some painful perception that we'll talk about, and gentle touch, things like, a gentle stroking or something like that. So those are our free nerve endings. Next up are our encapsulated receptors, and this is also what they sound like. They have some sort of encapsulation around the nerve ending itself, so there's a sort of extra bit to it. It's not just the free nerve ending floating around and picking up stimuli. There's some advanced sort of detection because of the encapsulation. So we have Merkel's discs, which are pictured here. These are important for our perception of form and roughness. We have our Ruffini corpuscles, which are important for static forces against the skin, so a constant pressure on the skin or stress. Those Ruffini corpuscles are pictured here in purple. We also have Meissner's corpuscles, which are important for edge contour detection, so detecting the edges of objects. Meissner's corpuscles are pictured right here. We also have the Pacinian corpuscles, which are these big things right here, which are important for our detection of vibration. I want to draw your attention briefly to table 7.1. This is a great way to sort of review the different types of receptors, where we can find them, and what they are good for detecting. So it's a nice reference if you want to sort of check yourself on what you know. Okay, let's speak in some more general detail about cutaneous senses and all the wonderful receptors that we have that allow us to experience the full bouquet of what a hot pocket has to offer, right? From the scalding hot outside to the frozen center, and perhaps even a little bit of spice. Let's talk about all the different things that our cutaneous senses let us do. So the encapsulated receptors that we have are mechanoreceptors, right? The movement of the skin results in movement of the receptor dendrites, which are located within encapsulated endings. So different stuff like pulling or pinching or stretching or vibration are going to differentially stimulate these receptors that are encapsulated to be very, very specialized. We also have temperature sensors. So two thermal receptor categories, including cold sensors, which are located just below our epidermis, and warmth sensors, which are located more deeply within the skin. So we're able to detect cold and warm with these temperature sensors that we have within our skin. We also have pain receptors, right? 3 different types of pain receptors, or nociceptors. We have receptors that respond to intense pressure, like striking, stretching, and pinching. We have nociceptors that respond to heats, acid, and things like capsaicin, which is a chemical that's found in things like hot peppers, and things that are like environmental irritants, things like inflammation-inducing chemicals that might be caustic. So sometimes this can get a little bit interesting. Some receptors respond to chemical stimulation as well as the presence of heat. So for example, the TRPV1 receptor, this is what capsaicin binds to. So capsaicin is the irritating compound that's in things like chili powder, chili peppers, which feels hot. So when capsaicin activates TRPV1 receptors, it feels hot. This receptor type also responds to temperatures above a certain temperature, so it can actually detect the presence of hot temperatures as well as spicy food. Likewise, the TRPM8 is responsive to the presence of menthol, which feels cool. So like some minty type tastes feel cool because this receptor is also responsible for the perception of cold temperatures. Okay, let's talk a little bit about pain. It doesn't seem like a great thing to have the ability to feel pain, but it turns out it's super useful and super adaptive. So pain, like thermoreception, is accomplished by free nerve endings in our skins. The perception of pain is thanks to those free nerve endings, though some high threshold mechanoreceptors can also respond to intense pressure, such as striking, stretching, or pinching. So really powerful pressure stimuli like that, pinching, stretching, striking, can be picked up by our high threshold mechanoreceptors that are in cat. We also have some free nerve endings that can respond to things like extreme heat, acids, and some chemicals such as capsaicin. So there are receptors specifically for all that kind of stuff that are associated with our free nerve endings that let us detect lots of bad things in our environment and give us a pain signal so we can avoid hurting ourselves with those irritants. So we've touched on this elsewhere, but I want to mention again that receptors are not evenly distributed throughout your skin. More sensitive regions have a higher concentration of receptors. So places like your hands and your face that are really, really sensitive in terms of touch have a much higher density of receptors. This is reflected in the distribution of our somatosensory cortex, right? Areas with more receptors occupy larger areas of the somatosensory cortex. So if you remember this weird little drawing of the homunculus laid over the top of the somatosensory cortex, this is just showing sort of a version of showing that the somatosensory cortex has space allocated based on how sensitive an area is. So your hands have lots of receptors, so they take up a lot of space. The back of your thigh does not have a lot of receptors, so it does not take up as much space. So if you want to test that, if you have someone that you're comfortable getting close to in terms of not having a social distance because you're living in the same place, take like 2 toothpicks or something like that and try a little 2-point discrimination task where you place the 2 points close together or far apart, very distance apart, and touch your willing participant in this experiment in a very sensitive place like the palm of their hand, and then try it again in a place like the back of the thigh or the back of their neck where their receptive fields are much larger. It's a lot easier to tell how close things are together, whether or not they are 2 points or 1 point, on an area with fine touch discrimination like the palm of your hand, versus something like the back of your neck, where it's much larger receptive fields. Basically, in an area that has a lot of touch receptors, one little touch receptor is going to be responsible for a much smaller area of real estate, right? So if you have a lot of sensors packed into your hands, that means you have really small receptive fields. So it's really easy to tell when 2 things are touching 2 different points. However, if you have much fewer sensory receptors, like in the back of your neck, each individual sensory receptor is going to be responsible for detecting inputs to a larger region of skin. Thus, if you have 2 points, 2 points can be touching the same receptive field further apart. So to put that a different way, in a less sensitive area, sort of like on the back of your neck, you might have 1 neuron that is responsible for detecting from a large area. And it can basically just tell you, is something touching me here or not? So if you have 1 toothpick touching that field or 2 toothpicks touching that field, it doesn't know the difference. It just says something is here. You have to put things pretty far apart on an area with big receptive fields to make sure that you're stimulating 2 different receptive fields. However, on something like your hand, where you have really, really fine receptive fields, 1 neuron is only going to be responsible for detecting stimuli in a very small area. So you have to get things really close together to be able to stimulate just 1 receptive field instead of 2. Okay, let's talk a little bit about your somatosensory pathways. So touch and pain/temperature travel along different paths. So while they're both coming in through the cranial and spinal nerves, they diverge after they enter the spinal cord. So here, at this point, the pain pathway crosses over to the contralateral side of the spinal cord and continues its descent that way, whereas the pathway that carries information like precise touch and kinesthesia stays on the ipsilateral side and goes up that. So these pathways reconvene after they're passing through the hindbrain into the midbrain. So they reconvene in the medial lemniscus, and after that they are projected onto the ventral posterior nucleus of the thalamus, right up here, VPN of the thalamus, and then from there information is sent on to the primary somatosensory cortex. So perhaps you've heard of phantom limb pain. This is a situation in which a patient has sensations from an amputated limb that is that's no longer attached to the body, right? So they have this feeling that their missing limb is still there. They report feelings of things like pain, pressure, tickling, odd temperatures, etc. And this is very distressing. I've heard some descriptions of it feeling like the toes crossed over in a way that is really uncomfortable and they can't uncross it, or that there's like a jabbing or stabbing sensation that's very painful. So they're feeling these sensations from a limb that's no longer. The neural basis of this is still debated. There are several ideas, one of which is that this could be a product of cortical reorganization. So loss of the limb will result in adjacent regions sort of moving into that territory. We've talked about plasticity and other sensory modalities. When one region of the brain is no longer receiving sensory input, regions nearby might take that real estate over. This could also be explained by difficulties in the peripheral nervous system. So improper inputs happening at the nerve endings at the site of amputation might be giving rise to sort of a dysregulated neural activity that results in the perception of weird signals that have no basis in reality being interpreted by the brain as problems with the missing limb. So I'll post a video on perusal about phantom limb pain and an unconventional sort of way of thinking about it called mirror therapy that provides surprisingly good results. Okay, just very briefly, we're going to touch on proprioception or kinesthesis. This is our ability to sense movement and position of individual body parts relative to one another. So this isn't something you think about very often, but without really thinking about it, you know where you are in space, you know how your body is moving around. As I'm gesturing while I'm talking to you, I don't have to think about or know where my hands are. I can feel where my hands are and how fast they're moving. This is all thanks to joint and muscle sensors that will send signals that coordinate with signals from other receptors like our eyes, skin, and our ears, so our vestibular cochlear system. All of that input coming in from our joint and muscle sensors coordinates with input from other things, other systems that help us know where we are in space to make us move around smoothly. We also have organic senses, so these arise from receptors that are around and in our internal organs. So like stretch receptors in your stomach letting you know that you're full, or other receptors that are part of other organs that give us sort of information about the state of those organs. This is nice to have, right? Because without our ability, our sort of kinesthetic sense, we would need to constantly watch our limbs or rely on information from other systems to coordinate our movements. In fact, people who have lost this sense have a really hard time moving around. They can't walk without watching their feet. They can't hold on to a coffee mug without watching themselves hold the mug. Without a real sense of where your body is in space and what you're doing, it's very, very difficult to get around. Okay, that's it for our senses of touch. Next time we're going to be talking about gustation.